Good morning, everyone. Welcome to our session on uncovering patterns in heavy-tail networks, a journey beyond scale-free, presented by Dr. Tanujit Chakraborty, and it's a joint work with Swarup Chattopadhyay, Dr. Kuntal Ghosh, and Dr. Ashit Kedas. Network is presented by a graph that is a function of nodes and edges. There are some static properties of real world networks, that is small world effect, degree distribution, triad and clustering coefficient, network resilience, and community structure. It also has some temporal or dynamic properties like densification and shrinking diameter. In network theory, the degree of a node in a network is the number of connections it has to other nodes, and the degree distribution is the probability distribution of these degrees over the whole network. Now, if we observe closely that real world heavy tail network, though claim to be scale free, but in real scenario, it doesn't follow power law distribution. A power law distribution can be defined as follows. A random variable x is said to follow power law if it has the following PDF. Px equal to k into x to the power minus alpha, where alpha is the exponent of the power law. There are few instances where people have shown that power law fitting in real world complex networks provide good flexibility. Just like in the work of Barabasi et al. In Science 2000, followed by Goldstein and Morris in European Physical Journal, and finally Closet in SAM Review 2009 paper. Now, a closer inspection of the degree distribution provide the followings. Most of the real-world habitat networks do not follow power law distribution. This is due to the existence of an identifiable nonlinearity in the entire degree distribution in a log-log scale. Just like in the graph, we can see in the log-log scale, the data actually do not follow power law distribution. Now, there are few recent controversies on this topic. Just like Stumpf and Potter in Science 2012 provide critical truth about the power laws. Bloido and Closet in Nature Communication shown scale-free networks are rare. In Nature Communication 2019, Holme shown it is rare but everywhere. Now, our observation is that degree distribution of real-world networks cannot be always fitted using a single power law distribution. So, we aim to find a new habitat distribution that can better fit the real-world habitat complex networks. To do this, we start with a brief details about Lomax distribution. It was given by K.S. Lomax in JASA 1954, is popularly used as an alternative to power law, exponential, gamma, and Weibull distribution for modeling heavy-tail data in the domain of business, economics, actuarial science, queuing theory, and internet traffic modeling. It is defined as follows. A random variable z is said to follow Lomax distribution with parameters alpha and sigma if the CDF is of the following form. Fz equal to 1 minus 1 plus z by sigma to the power minus alpha, where alpha is the shape parameter and sigma is the scale parameter, and both are greater than 0. Now, sometimes this Lomax distribution doesn't provide great flexibility in modeling heavy-tail datasets in its whole range. This paper proposes a new class of Lomax models where the non-negative shape parameter, that is alpha, is assumed to be expressible as a nonlinear function of the data for fitting these heavy-tail networks. We propose a new modified version of Lomax distribution. We name it as modified Lomax model, derived from a newly introduced hierarchical family of Lomax distribution for efficiently modeling the degree distributions in its whole range. Now we defined heavy-tail Lomax family as follows, where fx that is the distribution function of Habitel-Lomax model equals to 1 minus 1 plus x to the power minus mx. That is, we replace alpha with mx. That is, mx is a function of the data itself. And to make it a distribution function, we take some assumptions on the mx. The function m is strictly positive and have finite limit at infinity. That is, limit x tends to infinity mx equals to alpha. And these are few conditions that actually gives fx to be a distribution function. Now, the probability density function of Habitel-Lomax distribution family is as follows: 1 plus x to the power minus mx into the following function mx by 1 plus x plus m dash x into log 1 plus x for all x greater than 0 and equals to 0 when x is less than equal to 0. There can be a wide variety of choices of mx satisfying limit x tends to infinity mx equal to alpha. But we take the following choice of mx. We take mx equal to alpha into log 1 plus x by 1 plus log x to the power beta, where beta, if lying between minus 1 to 0, then mx approaches to alpha from below, and if beta greater than 0, then mx approaches to alpha from above whenever x tends to infinity. Now, modified Lomax distribution is of the following form: fx equal to 1 minus exponential of minus alpha into log power beta plus 1 plus x by sigma by 1 plus log 1 plus x by sigma to the power beta. Now, beta is taken to be greater than minus 1, and sigma is the scale parameter which is greater than 0, and alpha is also greater than 0. Now, we write this particular distribution function as MLM alpha beta gamma distribution, where alpha beta gamma are the parameters of the distribution. Now, these are the some plots of Lomax PDF. As you can see, Lomax PDF actually starts from 0, x equal to 0 to goes to x tending to infinity. And then this Lomax distribution, when we replace it with modified Lomax distribution, we can get several different functions like this. Thus, we can see modified Lomax model provides a more flexible PDF and CDF version, which will be helpful to model real-world network datasets. These are the plots of modified Lomax distribution function for varying values of alpha, beta, and gamma. Now, we provided the maximum likelihood estimation for the MLM model. This is the likelihood of the MLM distribution. And we can also find out a very interesting property for this MLM distribution. We found out theoretically that the above likelihood function, that is this L, which is a function of x and alpha, beta, and gamma, it has a global maximum for the samples xi at a finite point when the coefficient of variation of the dataset is greater than 1. Coefficient of variation for the dataset is defined by S by x bar, that is standard deviation of the data by the mean of the dataset. So for this network dataset, as we observed practically that the coefficient of variation is always greater than 1. Thus, these theoretical results have some practical implications. Now, we also shown some extreme value properties for the MLM distribution. In extreme value theory, we focus on extremes and rare events. This is a well celebrated topic in probability and statistics. So we have shown MLM distribution is tail equivalent to power law distribution, and MLM is a long tail distribution, and the distribution function of MLM distribution belongs to the maximum domain of attraction of the Frechet family of distribution. By Frechet, we means the family of Habitel distributions. Now, we have shown the application of the theoretical results and the developed model for several datasets collected from different internet sources. we consider standard data sets from different disciplines, namely social networks, collaboration networks, citation networks, web graphs, communication network, co-purchasing networks. These are the most standard data sets used for fitting habitat behavior of the real-world complex networks. Previous studies have focused to show the application of power law, Lomax, exponential, log normal, and other distributions for these particular network datasets. But they failed to capture the lower degree nodes while modeling these degree distributions. To overcome their drawbacks, we finally apply our proposed distribution to these particular datasets. So these are the parameter values for this particular datasets obtained by applying our MLM distribution. So as you can see, the S by mu, that is coefficient of variation for these datasets, are always greater than 1, which shows that our fitted model will always give a good fit for the datasets. And this is also clear from the chi-square value as we reported in the table. Now the experimental result shows MLM distribution provides better RMSE, KLD and MAE for all these datasets. So root mean square error, KL divergence and mean absolute error all are in favor of the MLM distribution in comparison to Lomax model, power law model, Pareto model, log normal model, Poisson distribution, power law with cutoff and exponential distribution for all the social networks we considered here, citation networks, collaboration network, web graphs, co-purchasing networks, and communication networks. As you can see, for the fitting of this particular network dataset in the log-log scale, our proposed distribution represented by the red lines provides better flexibility and also better fit for this particular network dataset considered in this study. As you can see, all the graphs suggest the same. Now, we provide some concluding remarks based on this work. We have proposed a new distribution to model the whole entire degree distribution of real-world complex networks which are heavy tailed. Our proposed degree distribution, that is modified Lomax model, results in better modeling the entire degree distribution of real-world networks. A sufficient condition for the existence of MLE for the parameters of the MLM distribution is shown using the coefficient of variation, that is for the dataset where CV greater than 1, our proposed MLM model will always give better fit. By simulating the parameters of proposed fitted MLM distribution, one can easily capture the spatial structure and dynamical patterns of a real-world network as the network evolves over time. There are few future research work from this topic, that is the dynamic pattern analysis of such group in real-world networks can be considered as a future work for this research. These are some selected references based on our study and those which we have discussed in this study. Thank you all and have a great day.